Hello, my name is Connor O'Hara, and this is Physics 2212 Lab 4. In this lab, we're going to be exploring the loop rule in energy conservation. We're going to be predicting the behavior of circuits containing resistors in series and parallel, examining the behavior of ohmic resistors and capacitors, and exploring the concept of and calculating the time constant of a circuit. Some physics concepts that we have to understand for this lab is the loop rule and the node rule. The loop rule states that the sum of voltages or potential differences across complete loops is equal to zero. And the node rule says that the sum of currents across multiple loops of a circuit is equal to zero. We also need to know Ohm's law. Voltage equals current times resistance. For part 1 of the lab, we first predicted the current in a series circuit given the voltage being 3 volts and the resistance being 147 ohms. We predict this to be 0.2 amps. When modeled inside of Circuit Simulator, we were able to find that this value was correct, and when we flipped the ammeter, the current became negative. Then we wanted to measure the potential difference with an ammeter, and found that it was 3 volts. The remaining ammeter became 0 though, because when we made this measurement, the voltmeter broke the current flowing through the circuit. The circuit was broken. We also wanted to find the voltage for each part in the path around the now closed circuit. After seeing this, we've determined that the sum is 0, and this means that the loop rule still works once we close the circuit. If we add an ammeter in parallel with our 100 ohm resistor, we can see that the ammeters now read 0.6 amps instead of 0.2. This is due to the node rule. The current is now split between the ammeter and the 100 ohm resistor. Since the ammeter has 0 ohm resistance in this simulation, the current goes through the ammeter and the total resistance is only 47 ohms from the smaller resistor up here. We can now calculate the resistance from each element in the simulation. For the R47 resistor, we're able to find that it has 47.95 ohms. For the R100 resistor, we're able to find that it has 102.05 ohms. And in this simulation, we have 0 ohms for both the wire and the ammeter. In part 2 of the lab, we studied capacitors. And when we model up a capacitor inside of our circuit simulator, we can see that as time increases on a charging capacitor, the light starts bright but then goes dim. When it's discharging, the bulb starts bright and then dims as well. The current, when we're discharging the bulb, is in reverse though. It travels in the opposite direction in the wires. The reason why the current slows down in both of these cases is that the charge on the capacitor increases or decreases, which means that the voltage across the capacitor increases or decreases, and correspondingly the current increases or decreases depending on whether we're charging or discharging. Using these observations, we measured the charge and discharge times for a 10 ohm and 20 ohm bulb. For a 10 ohm bulb, it took 10 seconds to charge and 12 seconds to discharge. For a 20 ohm bulb, it took 20 seconds to charge and 22 seconds to discharge. Since resistance is doubled, times for charging and discharging will also double. Using what we know, we can measure values at certain times after a charged capacitor is connected to a resistor to determine our RC time constant. The differential equation describing a voltage drop on a capacitor over time is listed below. If we take the natural log of this equation, we can see that a plot of ln delta V over delta V naught versus t will give us a straight line with a slope of 1 over RC. This value RC lets us know when our voltage difference is 1 over E. We can then plot our ln delta V over delta V naught data, giving us an equation equal to y equals negative 0.16 x minus 0.0016. The slope of the line must be equal to 1 over RC, and if we solve for RC, we can get RC equals 6.0034, which is very close to our expected value that we simulated in the lab. There's some exit questions that we must answer. What if we were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter? What's different about a real ammeter, and how would it have affected the circuits you hooked it up to? The ammeter would have had small resistance, so the current reading would have been smaller than the simulated value to cope with this fact. And what if we were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? If we had just the battery and the capacitor would have been charged immediately in the lab model. But in real life, everything has some kind of resistance, so the charge would not have been completely immediate. Thank you.